Have you ever wondered why raindrops don't fall at speeds high enough to hurt us? After all, gravity pulls everything toward the Earth. But raindrops actually reach a certain speed and don't go any faster. This speed is called terminal velocity. In this video, we'll explore how terminal velocity works, why it happens, and how an object's mass plays a role. We'll look at some fascinating real-life examples and dispel common misconceptions about falling objects. Let's dive in. To understand terminal velocity, imagine a raindrop falling from the sky. When it first starts to fall, gravity pulls it downward, causing it to accelerate. But as it speeds up, it also experiences air resistance pushing against it. This air resistance increases with speed until it matches the force of gravity. When these forces balance, the raindrop stops accelerating and continues to fall at a constant speed. This speed is what we call terminal velocity. It's like nature's way of setting a speed limit for falling objects. Now, let's look at some physics behind terminal velocity. Newton's second law, represented by F equals ma, tells us that force equals mass times acceleration. For a falling object, the main force is gravity, which pulls it downward. But there's another force we need to consider, the drag force. The drag force is represented by this formula. Here, CD is the drag coefficient, R is the air density, A is the object's cross-sectional area, and V is its velocity. As the object's speed increases, the drag force grows until it balances gravity. That's when terminal velocity is reached. Mass also influences terminal velocity. A heavier object, like a metal ball, has a larger gravitational pull, which means it takes more air resistance to balance it. This leads to a higher terminal velocity compared to a lighter object, like a feather. However, if we remove air altogether, like in a vacuum, there's no air resistance, and objects fall at the same rate regardless of mass. This was famously demonstrated during the Apollo 15 mission, where a feather and a hammer were dropped on the moon and hit the ground simultaneously. This formula shows how mass, drag coefficient, air density, and cross-sectional area determine terminal velocity. Parachutes are a great example of how terminal velocity can be controlled. When a skydiver jumps, they start in free fall, accelerating due to gravity. But as they reach higher speeds, air resistance increases until they hit terminal velocity. When the parachute opens, it drastically increases the surface area, adding significant drag force. This lowers the skydiver's terminal velocity, allowing them to fall slowly and safely to the ground. Without this increase in air resistance, their speed would be much greater and landing would be dangerous. Many people think that heavier objects fall faster, but that's only true when there's air resistance. In a vacuum, where there's no air, all objects fall at the same rate. But in our everyday environment with air, heavier objects often reach higher terminal velocities because they require more air resistance to balance gravity. This is why a stone and a feather fall differently in the open air, but at the same speed in a vacuum. To wrap up, terminal velocity is the constant speed an object reaches when the force of gravity is balanced by air resistance. We've looked at how an object's mass, shape, and the air around it all affect terminal velocity. Whether it's raindrops, skydivers, or even rocks in space, understanding terminal velocity gives us a fascinating look at the physics of motion and force.